Can you hear me now online? Okay, so you didn't lose much. I was just doing a recap about classical descriptive set theory. And so we say that given a polyspace X, analytic are the continuous image of closed subset of the bare space. We know that there are many characterizations. We just use, when I just mentioned this, again, it's going to be useful for in the generalized step. So now, what's the idea behind generalized descriptive set theory? Is to find an analog of the classical descriptive set theory when we replace omega with either kappa or cos kappa in a suitable way. Now, this is going to be our slogan, and I know that it's a bit different from many like on generalized descriptive set theory, where the setting usually replace omega with kappa. The reason is that usually in generalized descriptive set theory, we work on the assumption kappa to the less than kappa equal kappa, which is equivalent to require that kappa is regular and 2 to the less than kappa equal kappa. However, our approach is different, so we want to have a cofinality independent approach. So we want to work with kappa, which is both regular and singular. So we just assume that kappa is an uncountable cardinal that satisfies this assumption here. And so this means that we retrieve as a special case the regular case, so what is already known in generalized descriptive set theory, but we also extend the theory to singular cardinals. So now let's have a look at what our general counter and bare spaces are. So we consider the space lambda to the mu, so which is the all the function of mu, where lambda is an infinite cardinal theoretical, and mu is an infinite cardinal, and we endow this space with the bounded topology. So with the topology, which is generated by the cone NS, where S is a function from an initial segment of mu to it's called bounded because equivalently it can be defined by the cone NS, whereas is a function from a bounded subset of mu to lambda. So our generalized counter space is 2 to the kappa. So we just replace omega with kappa. The weight of this space is 2 to the kappa. This is just a quick computation. And here already you can see why the setup 2 to the kappa equal kappa makes sense, because in the classical case, we work with spaces of weight omega. We want to preserve some of the features, so here we want to work with spaces of weight kappa. And then the generalized is maybe a bit more delicate. In our setup is kappa to the cos kappa. So first of all, observe that this works also when kappa is singular, but when kappa is regular, then we go back to our space kappa to the kappa. And the weight of this space is kappa to the less than of kappa, which is kappa, and this is a consequence, again, of our condition on the cardinal. What is kappa to the kappa? So there are many reasons for that. The first is that when kappa is singular, the space kappa to the kappa has weight greater than kappa. So again, we are working with an object which is a bit different. And there are some other reasons that I will point out later. So here, you can see how we generalize the Borel sets and the analytic set. The generalization of the Borel sets will come later. But the kappa Borel sets are just the kappa algebra generated by the bounded topology. So we take the connection of all the open sets of 2 to the kappa, then we close under complements a union of size of kappa. And then we have kappa analytic sets, which are continuous image of closed subset of the bare space kappa to the cos kappa. Indeed, if kappa were singular, and if we were using the space kappa to the kappa, then we would get that every subset of 2 to the image of the generalized bare space kappa to the kappa. So now we see that this is a situation that we don't want because we would lose a characterization. Is it the microphone very annoying? No? Okay. No, but if it's okay for you, then okay. So an overview of my work. Okay, so in this table here, in the first column, you see some results that now we are going to discuss. And then we have 4 other columns. The first is classical descriptive set theory, and the last one is when kappa is uncountable and regular. The 2 columns in the middle are the case when kappa is a singular cardinal, first of countable cofinality, and then of uncountable cofinality. I want to just quickly say that all the results from the column kappa singular of countable cofinality are due to Monteros and Di Monte. Okay, and the blue boxes are the original results. So in the first line, we asked whether the counter space and the Baire space are homeomorphic. So in the classical case, we know that the answer is no. While in the regular case, it's a yes, if and only if kappa is not weakly compact. Now, when kappa is singular, this is just an observation. It happens that these two spaces are homomorphic because if you have a look at the natural bijection between the two, under the assumption that 2 to the less than kappa equal kappa, then you get actually an homomorphism. And even though I know that this may seem weird to you, actually, many of the things that work also in the singular case, I mean, all the results actually work thanks to these results here. So it's easy, it's really important. Then we have the Borel hierarchy. Also in the generalized case, it can be stratified into a hierarchy of length kappa. So what happens in the singular case is that you have a double hierarchy. So this happens basically because of this remark here. Because you can observe that when kappa is singular, kappa Borel set and kappa plus Borel set coincide. So one inclusion is trivial, while the other one works because, I mean, it's enough to show that the kappa Borel sets are closed under unions of size kappa. And if kappa is singular, then you can see that this holds because you can just take a final sequence and then split the union. So you actually stay in the kappa plus, in the kappa Borel. So those two are the hierarchy. I call them kappa plus and kappa just to distinguish them. And what's the difference? So the open sets are the same. The only difference is that here in the kappa hierarchy, you close under union of size kappa, while in the kappa hierarchy, you close under union of size strictly less than kappa. Now, yeah. So one more thing. So you can prove, like really using the classical argument, so using universal sets, that the kappa plus hierarchy doesn't collapse before kappa plus steps. And since we have this theorem, so that shows how the two hierarchies are related, we can also show that also the kappa hierarchy doesn't collapse. Now, I don't want to read this theorem, but I made a very ugly drawing. So as you can see, the two hierarchies coincide at every other step. So we have the open sets, which are the same, so also the closed sets. And then we have that sigma 0. Oh, yeah. So I must say that the blue is the kappa hierarchy, and the black is the kappa plus hierarchy. So what happens is that, for example, at even step, the sigma 02 kappa sets are closed under complement. So sigma 02 kappa coincide with P02 kappa. And these are strictly included in the delta 02 kappa plus subset. So this inclusion here is 3. Well, then at even step, sigma 03 kappa coincide with a level with sigma, in this case, with sigma 02 kappa plus of the other year. So we have one step when they coincide, and the other one when they do this special class, which is closed under complement. Okay, going on, then we discuss whether the analytic sets are continuous image of the Baire space. Now, this is true in the classical case because every closed set is a retraction of every closed subset of the Baire space is a retraction of the whole space, and the same hierarchy, but of course in the generalized setting, also holds when kappa is singular of countable cofinality. However, this is not true anymore when kappa is regular, and this is a result by Luke and Schlicht. And we were able to find, like following the same outline of the proof, we were able to find that the same holds when kappa is singular of uncountable cofinality. Then in the fourth line, we discussed whether the Sue's limit theorem holds or not. So the Sue's limit theorem says that the Borel set coincides with the analytic. Now again, the same outline of the proof of the classical setting that you can find at the K-quiz, substituting with the higher analog of the definition also holds when kappa is singular of countable cofinality. However, this is not true anymore when kappa is uncountable and regular. This was shown by Gitinen and Kulikov, so they were really able to find kappa, the analytic set, which was not kappa plus Borel. And again, we were able to prove that the same also holds when kappa is singular of uncountable cofinality. And then finally, we reach the kappa plus Borel star set. So the idea was due to Blackwell, because in the classical case, he showed another way to characterize the Borel set via games on well-founded trees. So now what we are doing is try to see what happens if we generalize this game and to see which kind of class we find. So the first observation is that when we work with kappa singular of countable finality, still we are working on games of length omega. So in this case, what happens is that actually, as in the classical case, Borel cell set, and the kappa B analytics coincide. While the inclusion are a bit different when kappa is as uncountable for finality, but first I will give you the definition. So very quickly, what is a generalized tree? It's just a non-empty partial order with a minimum, which is unique and we call root. And then we want that given every element of the tree, the set of all these predecessors is well ordered. And moreover, we ask that every chain of limit order type has a unique supremum. In particular, we are going to work with kappa plus of kappa trees. So with trees that have branches of length strictly less than of kappa, and such that all nodes have at most kappa many immediate successors. So what a Borel star code is a couple, is a pair TL, where T is a kappa plus of kappa 3. And yeah, we also need to add, this is just a technical condition, that every chain has a unique supremum. So if it has not a supremum, we add it. And then L is the labeling function that goes from the leaves of T to some Clopen subset of the generalized Cantor space. So we fix an element C in the Cantor space, and then we define now the kappa plus Borel star game on this code. So there are going to be two players, player 1 and player 2. They both start from the root of the tree, and then they take turns climbing up the tree, so choosing nodes. And they climb up until they reach a leaf. Once they reach a leaf, that in this case we call B, then the winning condition from player 2 is that 2 is if and only if C belongs to the Clopen set, which is individuated by this leaf B via the labeling function L. And we say that the set coded by this code TL is BTL, as it's the set of all the elements of the Cantor space, such that 2 has a winning strategy. So finally, a subset of the Cantor space 2 to the kappa is a kappa Borel star set, simply if admits a kappa Borel star code. So if A equals BTL from some code TL. Yes, also given a Borel star code TL, we can also define the dual. The dual is the set of all the elements. Dual of a code is the set of all the elements of the Cantor space, such that this one is one that has a winning strategy. Now, the dual usually don't coincide with the complement. So when it happens, we say that our code TL is determined, and so it means that the corresponding game is determined for every element C, because either player 1 or player 2 has a winning strategy in this case. Why are we saying that? Because we have this theorem here, which says that A is kappa B analytic, if and only if it admits a determined kappa Borel star code. Now, this theorem is a consequence of a higher analog of losing separation theorem, which was due to Meckler and Van Annen in the regular case, and then we work also in the singular case. Yeah, so this means that in particular, kappa B analytic sets are included in the kappa Borel star set. So here we go back to the chain of inclusion that we were looking at in the table. So the first, we have already discussed the first inclusion, and the second one is the corollary of what we have just said. Now, regarding this inclusion here, we still don't. It's still an open question whether it is consistent that these two classes coincide. So we know that it's inconsistent with kappa to the less than kappa equal kappa. So in the regular case, we know that it is consistent that these inclusions are proper. This was proved by Hittinen and Kulikov. However, the case whether it's consistent that they all are all the same is still open. Now, the last definition, we say that a code TL is unfair for player 1 if the dual of this code is the empty set. So it means that 1 has never a winning strategy. So either 2 has a winning strategy or none of the player has. So now, given what the unfair Borel star code, we ask two questions. The first one, are there kappa Borel star sets that admit only unfair code? And the second one, does every kappa Borel star set at least admit one unfair code? So the answer to the first question is no. Because every kappa Boresta set admits at least one unfair code, except for the whole space. While the answer to the second question is a little bit less straightforward, and the reason is if every kappa plus Boresta set admits an unfair code, this is equivalent to say that there exists an undetermined kappa Boresta code. So now we want to work towards that direction. So we ask ourselves if there exists an undetermined kappa Boresta code. And the answer is actually sits in a correspondence and an equivalence between the game steward game and the games, the kappa Boresta games. So here, with G kappa of kappa A, I denote a game steward game of length of kappa played on kappa, whose payoff is a subset of the generalized pair space kappa to the kappa. Now, this proposition says how these two games are related. So given a kappa plus Boresta code and fix an element in the counter space, then we are able to find a Kloppen subset of kappa to the kappa such that the two games are equivalent. And then we also have the other direction. So given a Kloppen subset of kappa to the kappa, then there exists a code such that for every element, the two games are equivalent. So as a corollary, we get that if kappa has uncountable cofinality, then there exists an undetermined kappa Boresta codes, if and only if there exists an undetermined long Gale Stewart game with Kloppen payoff set. But then here we are finished because in the classical setting, we know that there exists some undetermined Gale Stewart games. So this is a consequence of the existence of the birthday set. So it's enough to take this payoff to extend it in a way that we get a Kloppen payoff set, a Kloppen subset of kappa to the kappa. The two games are equivalent. This is really nothing hard. And so you can find that there exists an undetermined Gale Stewart game, and our question is settled. So to sum up what I've just said, given kappa an infinite cardinal and given B a kappa Boresta set, which codes are available for this set? So first of all, the case when kappa has countable cofinality. So we know that in this case, kappa Boresta sets coincide with Borel sets, which coincide with kappa B analytic. So in this case, we know that, okay, again, if the cofinality of kappa is omega, then there still holds the equivalence with Gale Stewart games, but this time they will have weight omega, so they are determined. So this means that in particular, we have also only determined codes, because also our kappa Boresta games will be determined. And then we only have fair codes. This is just a consequence of the first line. However, when the cofinality of kappa is uncountable, then this is the situation. So the first line, it admits just a fair code. This is the answer of question 1. Then there is our set B admits at least one unfair code. This was the answer to question 2. And then finally, there exists a determined code if and only if our set B is kappa B analytic. So I think I have some time. So I wanted just to quickly talk about further development of the work. So one possible thing is to extend the work that for the moment that we have done for counter and bare space to Polish-like spaces. So Agostini, Moteros, and Schlick find a way to define a generalized notion of Polish space. Actually, many of them. So it would be interesting to find study definable subset of this Polish-like space. And another development is to investigate the behavior of the wage hierarchy. I mean, modulo checking all the details, we already have a small result which says that if we consider saying that actually the wage semi-linear ordering on already fails at very low level of the hierarchy, but it's still open at actually a delta 0 subset of the counter space. And it's still open what happens in the regular case, and this is still a work in progress with the Schlick. Here you have some references, and that's pretty much all I have to say. I will leave you just the overview in case. Thank you. Can you say it again? Or slide 30. Here. Yes, because we can prove that every Borel set that meets at least one unfair code. Sorry, now I cannot. There are no sets that admit only unfair codes, except for if it's determined, then you know that there are. It's determined. It means that either player 1 or player 2 wins, so there cannot be an unfair code. The idea behind the unfair code is that you have your code, and then depending on the element of the counter space, of the generalized counter space that you pick, you know that either 2 has a winning strategy or no one has. So you have the dual, which is the empty set. But if we are dealing with determined games, then you know that either 1 or 2 has a winning strategy. Of course, not taking care of the case B is 2 to the kappa, because of course there's only 2 that has a winning strategy. Because when given a kappa Borel star sets, you mean if A is kappa plus Borel, then you write it this way from some code TL. So yeah, if the code is determined, then the complement is the dual, and so. No. No. I mean, when the cofinality of kappa is uncountable, with kappa's uncountable cofinality, then no. And also, if there are no other questions, I also wanted to add one very quick thing. So that having a look at this table, actually, what we can see is that the difference it doesn't really fit in whether kappa is regular or singular, but whether the cofinality of the cardinal is countable or uncountable. Indeed, the case when kappa is singular of uncountable cofinality, I mean, those results are more similar to the regular case rather than the case when kappa is singular of countable cofinality. And actually, this second column here really reflects very well classical descriptive technique. So yeah, maybe if the approach is to work more on cofinality rather than the regularity to work more on either whether the cofinality is countable or uncountable